very low PPAs. So with that, I'll stop there. And obrigado.
Thank you, Lincoln. Now I have the privilege to invite Professor Dalia Patino Echeverri, also of the Nicholas School of Environment of Duke University. She will talk about regulatory and commercial strategies to overcome the problem of intermittency. No, you have another title, that's okay too.
Boa tarde. I'm also going to speak in English. Not only speak on 3 or 4 words of Portuguese. So I'm going to tell you about the opportunities that there exist in the United States for battery energy storage to recover their costs, and how these opportunities have changed as the U.S. electricity markets redesign themselves to better accommodate the intermittency of variable energy resources. So I'm going to first show how battery energy storage systems can really need access to all revenue streams. The revenues from electricity price arbitrage are not enough. They were not in the past, and I'm going to show you some research we did before. They are not today, and it is very unsure they will be in the future. And the revenues from hybrid systems, like, for example, pairing this battery energy storage with solar, are also unlikely to cover the cost just by themselves. And then I'm going to discuss how these BES systems, battery energy storage, can recover their costs in U.S. electricity markets. And I'll talk briefly about the new FERC rule of last month, removing barriers for BES participation in U.S. markets, the implications for storage given the market design, and then some open questions that maybe Ethan can talk about from the legal standpoint. Okay. So the levelized cost of electricity of battery energy storages is still very high for all applications and all commercial technologies, although for peaker replacement it may be very competitive if you compare it with expensive peaking options. So in the past we looked at how these costs could be recovered through price arbitrage in 7 different U.S. organized wholesale electricity markets. We looked at 17 energy storage systems. This was looking at different parameters of the energy storage systems, and so in the bottom we have 3 energy storage systems that are mechanical: pumped hydro storage, compressed air energy storage, flywheels. Then we had 3 electrical energy storage: the magnetic energy storage, the capacitors, and the supercapacitors. And then we had 8 energy storage systems that use store energy chemically. And then each color is one different market in the United States. And this is the zero return. So then this would be where the energy storage system breaks even. And this is where it would make some return. And at the time, what we find is that only pumped hydro and compressed air and maybe Zebra batteries would be profitable. So it wasn't profitable then, and today we have looked again at this problem from another angle. This is also the work of one of the master's students, a master in environmental management at Duke University. This is data from using data from a solar wind farm, solar PV farm in California. It's an independent power producer that is struggling to recover costs. So this yellow line shows the average electricity price in dollars per megawatt hour that this farm, this solar PV farm is seeing at their location in the California system. And the green line is the average of their real power production. It's data given by them by this anonymous farm. And what you can see is that, low natural gas prices, high penetration of solar PV systems in California are really depressing these prices and are harming the opportunities for these independent power producers to recover their costs. And they are exploring whether pairing their system with battery energy storage can help them get better cost recovery. So you can see that at the times when the solar farm is producing the most, which is the green line, the prices are kind of in the lowest. So if they could shift and sell their electricity at the times of highest prices, that could be very advantageous economically. And if you look at the price differentials, so this is the average day-ahead price. I'll display what the day-ahead is later, and the average solar production. Now, it is, if you look at the price differential, so what is the difference between the highest price of the day and what is the difference on the lowest price in the day, and take an average for different months, you can see that the price differentials are significant. So this would signal somehow that there is an advantage, there is an opportunity in doing this price arbitrage with some batteries. So we explored this with very simple algorithm that assumes that we have a battery energy storage of between 0.5 megawatts and 50 megawatts of power capacity, and between 1 and 100 megawatt hours of energy capacity. We assume a cost of 369 kilowatt hours and round trip efficiency of 80%, 6% discount rate, and we assume the prices of 2016 that were observed at the location in the grid that is closest to this farm. And we took these prices as they were observed in 2016, and also inflating them so to make them more volatile, to make the differences between the highest and the lowest prices even 200% or 300% higher than what they are. And the algorithm was very simple. We just ask, is there, at any point in time, in hourly, we ask, is there PV energy available? If it is not available, then nothing is done. And if it is available, then we ask, is this, depending on how many hours of storage are we saying, but is this one of the hour, is this hour one of the lowest price of the day? And if yes, then you charge the battery. And if not, then if it is one of the highest price, then you discharge your battery. And if it is neither the highest or the lower, then you just keep the battery idle, and the PV power, generated power, goes straight to the grid. And what we find, so for example, this is, if you were using a system with 2 megawatt hours of capacity, then you would look at the prices, and the charging would happen at these 2 hours. Sorry, this charging would happen at these 2 hours. No, sorry, charging would happen at these 2 hours, which is this brown line shows the prices. And then this charging, so the energy storage system would be putting that energy into the grid, would happen at these 2 hours. And we do that for all the combinations of power and energy capacities for the whole year, optimizing the system capacities. And we find that only a small system of half a megawatt and 1 megawatt hour of capacity would achieve a net present value of about $200,000 over 15-year time span. But none of the other battery energy storage systems would break even. They would all incur costs. None of them would improve the economics of the solar PV plant. We looked at what if instead of California prices, we had prices of PJM or ERCOT, and even if the price differentials increased by 300%, this wouldn't make it. So clearly, just electricity price arbitrage can be beneficial for some hours, but it cannot be the only source of revenue. And luckily, it is not the only one. So the battery energy storage systems and any other technology for energy storage can participate in wholesale organized electricity markets, or what are called, for short, ISO-RTO markets. they can participate in energy markets, providing energy, providing reserves, and providing RAM capability products. They can participate in capacity markets, and they can participate in ancillary services markets. And this is already possible in several ISOs and RTOs, and soon it's going to be the rule everywhere due to this FERC Order 841 that was released in February 15. However, it is still unclear how a specific RTO ISO rules that are going to be modeled after this FERC order will really enable all the opportunities for the ESRs, energy storage resources, ESRs. So Dr. Mooney showed the different RTOs in the United States. It's more than, well, a very good part of the territory and the electricity sold in the United States goes through these wholesale organized electricity markets. And they are regulated by FERC, the Federal Energy Regulatory Commission, and which issued this order that gives 270 days to the RTOs, ISOs to create and file a participation model for energy storage resources, or ESRs. And after this, they will have 1 year to implement the changes. Now, energy storage resources already participate in energy and ancillary services, but they have to use models that are not necessarily designed to take advantage of their unique characteristics, their fast ramp rates, their precision when responding to dispatch signals, etc. So the full potential of these energy storage systems cannot be utilized in the markets. So the intention of this FER rule is to have a very clear definition of these systems and to make sure all the barriers for taking advantage of the great characteristics of these technologies are used into the market. So FERC defines ESRs as resources capable of receiving electric energy from the grid and storing it, and then later injecting it to the grid, back to the grid. Now, if the energy was consumed behind the meter, so like it was stored and then consumed, then that's already, batteries can already participate doing that, providing the services through the rules that govern demand-side participation. And all types of energy systems are considered regardless of their size. So FERC says that the ISOs, RTOs will have the freedom to decide what is their minimum size, but it shouldn't be larger than 100 kilowatts. So it could be very, very small sizes. Any storage medium is to be considered, and any location is also be considered, whether it is in the interstate grid, in the distribution system, or behind the meter. Now, so FERC has established 4 guidelines, 4 very broad guidelines for these models or participation models that the ISOs and RTOs have to design. So the first is that these participation models have to enable the ESRs to provide all the capacity, all the energy, and all the ancillary services that they can technically provide. If, of course, RTOs and ISOs can decide what are the technical requirements. For example, an ISO can say that an energy storage system could only participate in frequency regulation if it has an automatic governor control, automatic generation control. Also, FERC says that it should be allowed for energy storage system to set the prices. They should be able to set the prices as buyers of electricity or as consumers of electricity. They should also be eligible to make whole payments. So if they are dispatched at a point that harms their economics, as for sometimes happens to generators, they should be able to have a payment outside of the market mechanism so that they are make whole and not lose money. And then the bids that these energy storage systems submit to the operator are similar to the complex bids that generators submit now. So generators say what is their maximum and minimum capacity, what is their ramp rate, what are the reserves they can provide, what are their marginal costs. So storage is also going to have to or should be allowed to submit all these parameters. What is their state of charge? What is their maximum or minimum state of charge? The limits for charging and discharging, the timing, the runtime, and the ramp rate. And finally, the energy storage systems should be able to buy and sell electricity at the locational marginal price. And I'll explain that in a second. But they have to, they'll have to use, okay. So how do the markets in the US work, and how will they have to be perhaps redesigned so that they can accommodate these models for participation of energy storage systems? So as you know, balancing supply and demand at all times, as all energy systems have to do, requires planning at all time scales. So it requires, if you're talking about vertically integrated utilities, then it requires infrastructure planning and construction that starts between 1 and 10 years ahead of the delivery of the electricity, and then the operational planning. And then there is generator scheduling and generator commitment, and finally the operation. You need the operating reserves to be able to balance the demand and supply in real time. With markets, you have to meet the same functions. You have to keep this balancing act at all these time scales, but with markets, with different markets. So you have the capacity markets planning for the resource adequacy, making sure that at all times there is enough capacity installed to meet your highest peak plaza reserves. Then you have a day-ahead and real-time market to deal with the daily balancing, and then you have the ancillary services markets to deal with the shorter time spans. So this day-ahead and real-time market are what is called a two-settlement system. So we have it's two-settlement because it happens in two stages, the balancing of demand and supply. So in the day-ahead market, there are hourly market clearing prices that are calculated for each hour of the next operating day, and they are based on the demand bids and the generation offers, and on any bilateral schedules that there may be in the system. Now, in the real-time balancing market or the spot market, then the clearing prices are calculated every 5 minutes, for the most part, based on actual system operations. And the generators that are capacity resources will receive capacity payments, and they will have to submit their offers in the day-ahead market, and they also need to tell the ISO what their availability is for the next 7 days. Other generators can just choose between the day-ahead or real-time or work on both. Now, depending on the market, there may be one or more other instances in between these day-ahead and real-time. And all these price calculations are based on locational marginal pricing, which means prices depend on the node in the network, the place in the network where you are. And if there was no power transmission congestion, all the prices would be the same. But because there is often this congestion, then those prices, LMPs, represent that. And nowadays we talk about extended locational marginal prices, which is meant to incorporate some of the costs that are not covered in these LMPs, which is, for example, when you have to keep a power generator running at their minimum runtime, not because they are the cheapest generator in the fleet, but because their operational constraints don't allow to shut them down. So they cannot save the price, but they are still running. There is some pricing that needs to go there, so that both markets are clear with a unit commitment and economic dispatch algorithm that co-optimizes energy and reserves. They find how much to commit and dispatch. Yeah, and find what is the power output produced by each generator, what are the reserves. If these are markets for ramp capability, and I will explain what this is, then they will also find what is the ramp capability procured by each generator. And they find prices for all these things. And of course, the these are optimization models. So the shadow prices of the constraints for demands, for reserves, and for ramp capability products find the prices of each of these. And the generators will be paid for energy, for reserves, and for the RAM capability that they produce both, that procure to the system both in the day ahead and in the real time. So now what we are saying is energy storage systems can, and any energy storage resource can participate in these markets, and so they will be getting payments through all these mechanisms for energy, for reserves, for RAM capability. They're providing it in the day ahead and in the real time. So what are RAM capability products? So these are products that were implemented in MISO in 2016 and in CAISO as well. They were meant to deal with this duck curve. They are proven in their short time span, and with we, for example, did some research looking at what are their economic, environmental, and reliability outcomes with these systems. It's proven that they reduce instances of energy and reserves scarcity, and they reduce CO2 emissions. They slightly increase the prices during the non-shorted periods, but then decrease the prices during the times that were before shortage periods. So then they reduce these price spikes. They therefore provide a transparent price signal, and these prices reflect either the marginal cost of producing this or providing this RAM capability, or the demand curve, how much the system operator is willing to pay for this RAM capability. So how does it work? It was considered, for example, that we are dispatching in 10-minute dispatch intervals. This is what we did in our paper because our wind data was only every 10 minutes, although we had market data for every 5. And so this is the previous dispatch level. This is now the period we are dispatching. This is the forecast net load. So this is the expected ramp. This is the expected ramp. Now, however, there is uncertainty on where this will really be the net load. So it could be lower, it could be higher. There is this uncertainty up, and there is this uncertainty down. So this is going to be the up ramp capability, and this is going to be the down ramp capability requirement. And so the way it's going to be provided in the system is by now. So if we have ramp, we add these red terms in our day-ahead unit commitment algorithm or optimization model. So what we are doing is minimizing the total cost, and that includes the cost of energy and the cost of reserves, the cost of starting units, the fixed cost operations, some penalties that we have for over-generation and under-generation, and for over-reserves and under-reserves, so that we make sure that the model converges, and then benefits of these procured RAM products. And we make sure that the procured ramp capability is less than the target that we have, and that we procure it with all the generators. And we do the same for the economic dispatch, and that way we get the pricing. So the pricing will be given by either the marginal cost of producing this ramp capability or by these URC benefits. These URC benefits are usually lower than the under-generation penalty or the scarcity of reserves, because this is like third in priority. You first want to meet your energy, then you meet your reserves, and then third you have your RAM capability. So as I said, the shadow prices will tell us what the URC and DRC are. Okay. So the question is, does this, so as you can see, we are co-optimizing. So we are saying that in these markets, no resource has to say how much RAM capability wants to offer to the system. They just have to say, this is my energy offer, this is my reserves. The RAM capability will be scheduled by the system operator as it is optimal for the system. So does this hinder ESR's participation? Well, so none of these, either CAISO or MISO in the RAM capability products, ask for any explicit bids. You assume that the generators agree to provide whatever service is deemed to be optimal for the system. So should ESRs submit energy bids? So how is this going to work? In the end, FERC said we are going to let it let ISOs decide, and we will see what happens. Because changing the way these markets work and going away from this co-optimization, the way this works would imply changing software and changing things that are done. So probably with time, this rule will change or will be amended. But FERC encourages ISOs to look at this. Now, so capacity markets. Well, this is the other revenue stream. So energy, ancillary services, capacity markets is the third revenue stream for markets, for ESRs to recover their costs. So many of these capacity markets have different requirements. So should the ISOs allow ESRs to derate their capacity, and if they needed to meet minimum requirements at ISOs. So for example, a 10 megawatt or 20 megawatt hour ESR can offer 5 megawatts of capacity into a capacity market that has 4-hour minimum runtime, and that way it can meet the requirements. So FERC has said this is what should be allowed in all markets. Of course, ESRs should still be accountable for penalties for non-performance like any other capacity resource. They shouldn't use this re-rating as an excuse for withholding capacity and playing strategically in the market. ISOs will be able to propose their own rules. For example, New York ISO has one that says that ESRs should be limited to one 4-hour interval per day. And the capacity markets have already been changing and really favoring ESRs. For example, CAISO has already moved away from just talking about having enough capacity to make the highest peak and saying, well, this capacity is better if it has at least a portion of that is a flexible capacity that can respond to real-time instructions, that can start at least twice daily, and that is responsive enough to meet anticipated ramp needs. So the other issue with this participation of energy storage resources in markets is that they can provide these services that can be market priced, and they can also defer investments in transmission and the distribution system, and these may be paid or compensated with regulated payments. So this could put ESRs in a position of advantage relative to other resources that only recover their costs through market mechanisms. So if there is a potential for market distortion, this is something that ISOs, RTOs, and FERC would have to look at. And who can own these ESRs? In the US, the backbone of this restructuring system was unbundling unbundling the different systems, splitting the ownership of different resources. So how could this put some players in a position of advantage? That's another question. So in conclusion, we can say that oh, actually, I was showing this. Whoops. So ESRs can recover costs through market mechanisms, the inherent real-time markets, through capacity markets, through ancillary services. They can have cost-based rates, and it is still to see. We need to see what the implementation of these models for participation will bring. We know that variability and uncertainty of ERs is motivating lots of changes in US markets. Flexibility is valued and it is paid for. RC products are one example. But at the same time, these RC products and other incentives for paying for flexibility will inevitably reduce price volatility. So this will reduce some opportunities for price arbitrage. And there are non-trivial modifications that are required to these markets if we really want to guarantee that they don't pose any barriers to energy systems. So lots of questions and lots of interesting things for us to see in the next 9 months and 2 years when this is implemented. Obrigada.
Thank you, Dalia. Eu tenho que dar um aviso